This is module number 8 from my online Introduction to Tensors for Non-Mathematicians course. This module is titled Linear Maps. So what are we going to discuss here? There's a lot in this section, I'm not going to lie, so we're going to list it off. We begin by defining a linear map as a tensor-based functional relationship between two vectors within a primal space. We're going to compare the linear map to the dual vector, which we can also call the linear form. Now, both of these objects apply some mapping or functional relationship to an input primal vector. We're going to discuss how a linear map may be decomposed into its coordinate as well as basis components, and this is similar to how we treated both the primal and the dual vectors. We're going to discuss the relationship between the basis associated with the linear map as well as those associated with its respective input and output vectors. And we'll see there's a pretty strong relationship there. And then we're going to discuss how to define both pure and impure matrices. These may be new terms. How to define both pure and impure matrices as a linear combination of vector-covector pairs, or we could say column-oriented and row-oriented array pairs, or more appropriately, tensor products, but we'll introduce that term later. We then discuss how to define both pure and impure matrices as a linear combination of vector-covector pairs, or we could say pairs or products of row-oriented and column-oriented arrays. And what we'll see is that we can generate the linear map type tensor in a similar manner. As the course title suggests, these videos are aimed at those with interest in science and engineering, with some background in linear algebra who want to learn more about tensors. I have written a text to accompany this set of PowerPoint lectures, these sets of videos. A link to that text will be provided in the description below when it's available. Still, as usual, working on publication details. If you have any questions, comments, corrections, please place them in the comment section below. I'll try to address them as quickly as possible. As always, please like and subscribe to see more engineering and general STEM educational videos. Let's discuss linear map type tensors. This is the third type that we're looking at in this set of lectures and these set of online modules. The first two were the primal vector and the dual vector or the covector. So the primal vector, denoted by V arrow hat, is composed of a covariant basis set B arrow hat and a contravariant coordinate array V with no arrow hat. The second type of tensor is the dual vector or the covector. It's composed of a contravariant basis set beta, left facing arrow hat, and a covariant coordinate array gamma, no arrow hat. So we see a common theme here that both of these tensors, right, can be composed of some coordinate set as well as some basis set. Now we move on to a third type of tensor, the linear map type tensor. We're going to denote that by an uppercase M, bold, okay, because it is an algebraic structure, and it will have this bidirectional arrow hat, which we'll talk about where that comes from in a second. Now, just like the first two types of tensors, the linear map may be composed of two other pieces. It also has a coordinate matrix instead of a coordinate array, and a basis matrix set, as opposed to up here we had a basis vector set and a basis covector set. Now, one main reason for the difference is that both of these, the vector and the covector, the primal and the dual vector, right, are rank 1 algebraic objects. So as such, their components are similarly rank 1. This is why we can classify the basis set of the primal vector as strictly covariant, right, because it forms a row-oriented array-like object. The coordinate array forms a column-oriented array-like object, and we could do the same thing for the dual vector. So because the primal vector is rank 1, its individual components will similarly be rank 1. The linear map is rank 2. So that's why its coordinates are stored inside of a matrix, a rank 2 matrix, as opposed to rank 1. And that's the reason why its basis set is composed of matrices, or actually, to be more accurate, they're composed of tensors, of linear map type tensors. And they are defined by the tensor product of two other basis sets, which you can see here, one being primal, one being dual. Let's forget about that for a second. We're going to come back to it. I do want to talk about notation. So we refer to the tensor, again, with the bold uppercase letter, with the dual or the bidirectional arrow hat, and that is not equal to simply the bold uppercase variable with no arrow hat. This is the linear map type tensor, and this is just a matrix, but in this case, we're assuming it's the coordinate matrix associated with that tensor. So we're going to explain later what these components right here mean, and specifically how we can combine them together to create a tensor, because it's a little bit more complicated than the situation for the primal and the dual vector, where we simply have to take a contracted product. So continuing on with this question of what is a linear map. So the linear map defines some linear functional relationship between two primal vector spaces, such that the operations of vector addition and scaling or multiplication are preserved. So what we see is that some linear map type tensor M allows us to map from primal vector space A to primal vector space B. Unlike a vector, a linear map represents a function as opposed to a value. So if I were to create a little table here, right, so far we've seen the primal vector predominantly represents some value in the n-dimensional space. Okay, the dual vector, which we're going to see later on, could also be called a linear form. Okay, what that does is that maps some vector space to a scalar, and the linear map, okay, right, maps some vector space, primal vector space, to another primal vector space. So unlike the vector, the linear map is functional, not a representation of a value, at least not in the way that's generally interpreted. And unlike a covector, which yields a scalar output, the linear map generates a vector. So on the grand scale of things, you can think of the linear map more resembling the dual vector. We use the bidirectional arrow hat to represent rank 2 plus tensors, okay, which may be composed of vector-covector pairs. And we're going to talk about what a vector-covector pair is a little bit more later. Essentially, for rank 1 tensors, right, we can denote them as either, we can use right-facing and left-facing to tell us whether it's primal or dual. But once we get above rank 2 plus, essentially everything will have both co and contravariant components. So that's what the bidirectional arrow hat kind of represents. And it also provides us a way to distinguish between coordinate algebraic objects and their tensors. So here we have an example of an expanded linear map, meaning I expanded it, showed all the pieces. It uses the same notation that we've seen previously. So the tensor is represented by an uppercase bold variable with the bidirectional arrow hat. The individual elements are going to be italic and non-bold. They keep the arrow hat. And then we use the same, right, contra and covariant indices to represent individual elements within the linear map. And so you can see here, this is an n sub b by n sub a matrix or linear map, and we represent that using the same symbol we've seen in previous lectures. So script R tells us that it's composed of scalar real numbers. The height is NB, okay, and the width is NA. So this is a rank 2 object. It has a contravariant rank 1 and a covariant rank 1. These two numbers should add up to give us that number. All right, now let's take a slightly different view. Let's look at the input-output relationships. We've already said that tensor M, linear map M, can be used to map some vector space A to another vector space B. Okay, both being primal. The most basic representation of that is right here. Okay, we can simply say that VB, just going to write it, is equal to the linear map M times VA. Now note that these are all tensors. We can expand that, however, and that gives us the representation shown here. It looks a little bit cluttered, but it does a good job of, I think for those of us that are not so familiar with the type of notation, it allows us to peek inside of these algebraic structures. Anyway, so let's break this down. So here we have the blue underlined output or resultant vector, VB. Now, as we've seen before, it's composed of a coordinate array, a contravariant coordinate array, which we call V pre B, meaning that's, spoiler, before we're going to apply some sort of change of basis transform. And it has its associated basis set, which we call B pre B. Now, if you remember, this is called a standard. They are called standard basis. We also call them the orthonormal basis. So essentially, this is an identity matrix. Now, that's obviously not a requirement for any type of linear map tensor, but it's going to make our explanation here a little bit easier. Now, flipping over to the green underlined component, which is the input primal vector, same thing. We have a contravariant coordinate array, which we call V pre A, and then the covariant input basis set B pre A. Now in the middle, we have the tensor M. And we've already explained what's going on here, so I don't think I need to go through the individual elements. Now, one thing you'll note is that, and let's take a sidestep away from tensors for a second and just look at this using our linear algebra brain. Yeah, I can really think of this as like, well, the identity matrix really isn't doing anything, so I can get rid of that. And what we end up with is what looks like a regular old matrix equation, right? Where we're taking a square matrix or rectangular matrix and multiplying by some array and then getting another array. So this math should not be too foreign as compared to what we've seen in the past. So the input vector, I just clarified this down here, is composed of the basis set, its associated basis set, and coordinate array. Same thing over here. Now, I did want to talk about this notation really quick because we're going to use it a little bit more later. So we have a coordinate array that we call V pre A. Now, this is really a version of the coordinate array VA, except it's for the specific case where we have the pre-transform basis. So we use a slightly different notation at certain parts, where instead of saying V pre A, we can say that's equal to VA, except we're going to add these brackets as an additional subscript. And inside the brackets is really just telling us what basis set this is associated with. So whereas we kind of assumed that V sub pre A is associated with the basis B pre A, as shown right here. We can explicitly show that using this subscript. And when we get into more complicated tensors where we have tons of different coordinate arrays and tons of different basis sets, this can make it a little bit easier to define the coordinate arrays, so we don't have to constantly remember what is what. Okay. So, let's talk about the coordinate matrix-based input-output mapping. So we talked already about the tensor-based mapping. Can we redefine this in terms of traditional matrices? We're going to see that we can. Now, we did something similar to this when we were talking about primal and dual vectors as well. If you remember, we said that we could take, this output, which is a scalar z, and that's equal to our our covector array times our covector basis set. So that is some covector, and we can multiply that by the basis set times the coordinate array. That's equal to some primal array. These can cancel out if we set them appropriately, and we end up with a strictly coordinate-based expression. So I don't know if that made sense, but that's what we're trying to do here. Can we redefine our tensor-based expression in terms of simply the coordinate matrices? Can we generate an input-output mapping with regard to strictly those? So like the coordinate array associated with the primal vector or the dual vector, dual covector, a linear map has an associated coordinate array, and we've already shown this. This coordinate matrix M, no arrowhead, maps one array to another, v pre A to v pre B, whereas the tensor maps one vector, one primal vector to another. So that's the difference here. Okay, we can create an expression which relies on a tensor and maps one tensor to another. That expression would have its information about its axes, referential directions, basis baked within it. Or we can define a similar relationship that is based on a coordinate matrix, and that maps one array to another. And within this expression, we wouldn't have any information about the referential directions, axes, bases. Now, how can we derive an expression that's similar to this, or that looks like this? What we have to do, and we're going to show this on the next slide, is we're going to create matrix M. We're going to calculate it by simply grouping the basis sets from both the input and the output arrays with the original tensor M. So if you remember, we had something that looked like this, right? B pre B, this is V, B is equal to, and then we had our linear map type tensor, and that's multiplied by V pre-A, VA, right? This is our tensor. This is also our tensor. Now, all we have to do is we can multiply by the inverse. We'll stick that in there as well, so I don't have room for it. So that goes away, and what we end up with is a relationship between the arrays. That's a B. All right, so here we have a relationship between the coordinate array VA, the coordinate array VB, and we are going to call this the coordinate matrix associated with our tensor. All we did was just take the basis set from the left-hand side, invert it, move it over to the right-hand side, and then group these things together. Okay, so like I said, this will require matrix inversion. Unlike a tensor, the coordinate matrix of the linear map is dependent on the basis of its inputs and outputs. Okay, B pre-A, and that should be B pre-B. It is variant to change of basis. So if you look here, right, this tensor is invariant to change of basis. This matrix right here is very much variant, changes with the basis, because you can see the bases are embedded within the coordinate array itself. So if this changes, then this is going to change. If this changes, then this is going to change. And what we're going to see, to take one step further, is that the basis of the linear map are ultimately determined by the basis of VA and VB. All right, the linear map needs to have appropriate bases that allow us to map from primal space A to primal space B. So here we have a more formal version of the equation that I just hand wrote on the previous slide. I don't want to go down any rabbit holes here because there's a lot on this slide. So let's try to focus on the most important things. First, this equation, right, provides a relationship between, let me change my color here real quick to the orange that I've been using, between the output coordinate array and the input coordinate array, right? This is similar to the tensor-based relationship we saw previously, where VB was equal to M, except now we have the bidirectional arrow hat indicating that that was the tensor, times VA. So we can write this in terms of coordinates, or we can define this in terms of tensors. This is very similar to what we saw for the primal vector or for the dual vector, right? We know that we can define a primal vector, right? That's the coordinate array. So we have the tensor, basis, coordinates. We can reverse that and we end up with, I just keep putting the X there to remind us that it's not the tensor. That can be the basis set inverted times the primal array. So this relationship right here, okay, is analogous to calculating our M no arrow hat. And we show how that is done essentially inside of these parentheses. So M no arrow hat is equal to B pre-B inverted times the original tensor times V pre-A arrow hat. So both of these equations demonstrate that for a tensor, any tensor, we can decompose it to two components, right? Now, they're not always going to have the same shape and the same form, but we can decompose the tensor into its coordinates as well as its basis. And so there's analogous relationships between all the different types of tensors that we've taken a look at here. I think the rest of this equation is either self-explanatory or something that you can take a look at on your own. So I'm actually going to pause this module right here and sort of declare an intermission. We're going to split this module into two parts. They're not going to be separate modules. I'm not going to call them Module 8 and Module 9, but actually Module 8A and Module 8B, because they don't really stand alone from one another. The first module, the one we just finished, or the first part, provides an introduction to the linear map and describes the basic input-output mapping that defines it. But we didn't really have a chance to dive into the definitions of its components, and that's what we're going to do in Part B. So Module 8B, which there'll be a link to below, is going to dive into how the coordinate matrix, and more specifically the basis of the linear map, are defined, and how we can define the linear map type tensor as the linear combination of the basis sets, as we will define in a couple of minutes.